Okay, welcome back. We are now going over the 9.3 homework on regular grammars, which I thought was sort of hard. Let's go. I just did the entire homework all fresh and new. So this should be smooth and without error. Okay, number 5 said, I guess I could have written this in advance. Number 5 says, hey, take the following, well, I can just have it here on my paper. Number 5 says, take the following alphabet, sigma, which consists of zeros and ones, and, okay, let the set of non-terminal symbols be S, X, Y. I don't even really need to be told that. And then I personally find the OR notation to be extremely distracting when there are zeros and ones in my alphabet. So I'm going to just write it out long style as S goes to 0, 1, X, S goes to 1, Y, X goes to 0, X, X goes to 1, Y goes to 0, 0, Y, and Y goes to 1. Alright, so I very ambitiously decided to try to understand this grammar first before answering any of the questions about it. And so that's what I did. Let's go. Okay, so if you present me with this regular grammar and I want to kind of trace it, I'm going to make this sort of decision tree. Well, I start with an S, say here, and now there are two options. There is the option to follow this rule or this rule. So if I follow the O1X rule, I get whatever I get. If I follow the 1Y rule, I get whatever I get. And okay, I think I know what's going on, because what is Y? Let's do that first. Y either produces 0, 0, Y or 1. And so one option is that this Y gets replaced with a 1, and another option is that Y gets replaced with 0, 0, Y. So I get 1, 0, 0, Y is one thing to do with that Y. But now, once again, I can replace that Y either with a 1 or with a 0, 0, Y. And okay, I think it's now clear what's happening, right? Every branch, either I replace that Y with a 1 or with another. Now I'm going to have sort of 6 zeros and a Y there. And this just kind of continues. Okay, what about the other option? Now, what does X do? Well, X either sort of terminates in a 1 or it gets replaced with a 0X. So now I have, let's see, that X could just be a 1, so we could just end up with 0, 1, 1. But we also might end up with 0, 1, and instead of that X we get 0X. And here, that X could get replaced with a 1, or it could get replaced with 0, 1, 0, that X could get replaced with 0X. And again, 0, 1, 0, 0, 1, or 0, 1, 0, 0, 0X. And okay, I guess I should stop. I'll do sort of just like one more or something. Once again, that X gets replaced with 0, 1, 0, 0, 0, that X gets replaced with a 1, or 0, 1, 0, 0, 0, 0X, etc. Okay, so that was a little chaotic space, planning out my space wise, but it looks better on my paper anyway. What have I learned from all of this? What I've learned from all of this is that I think I can now describe all the strings that this language generates pretty smoothly. Either there's sort of this immediate branch that happens. So either the string starts with a 1. Well, the string is gonna, one option is that the string starts with a 1, and then there are either going to be 2 or 4 or 6, etc. zeros in the middle. So I write that 0, 0, star, and then I have this this language now, I guess, to describe these strings. Yeah, I do. And followed by, it's always going to end in a 1. So that's one option. But then, so okay, I'll just continue to use sort of or now, maybe I guess I will. And what's the other option is that the string starts with a 0, 1, and then it's going to definitely end in a 1, because that's the only way the X non-terminal ever terminates. But now there are going to be some number of zeros in the middle. So 0, 1, 0, star, 1. So basically the string either begins with a 0 and a 1, some number of zeros and a 1, or it begins with a 1 and some even number of zeros followed by a 1. Okay, so I am very happy now, and I'm ready to do this problem. What does the problem say? It gives me 5 strings and asks me whether these strings are in the language or not. And the first string is, so I think I'll just like do this or something. So the first, well, I'll just list the, let's see, I'll list the strings. This is 5. So 0, 1, 1, let's see, B, C, D, E, something like that. So 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, and 0, 1, 0, 1. Directions are, tell me whether these strings can be generated, and if so, produce a derivation. I sort of have done all the hard intellectual work kind of already, and so can I generate the string 0, 1, 1? Yeah, I can. Boom, there it is. Can I generate the string 1, 0, 1? Well, no, because if you start with a 1, then there need to be an even number of zeros. Can I generate the string 1, 0, 0, 0, 0, 1? Yes. Can I generate the string 0, 1, 0, 0, 0, 1? Well, yes, because if my string starts with 0, 1, I can have any number of zeros in the middle. In fact, that string appears right here. Can I generate 0, 1, 0, 1? Yes, I can, because that's just there. Okay, so I'm very satisfied. I don't really want to produce these derivations, but okay, I made you do it, so I guess I should too. Here's the derivation. S goes to 0, 1, x, and then I replace that x with a 1, and so I get 0, 1, 1. Okay, good. This one can't be done. This one, I replace s with 1y, then that y gets replaced with 1, 0, 0, y. Then that gets replaced with 1, 0, 0, 0, 0, y. The y gets replaced with 0, 0, y. And finally, the y gets replaced with a 1, so it's 1, 0, 0, 0, 0, 1. Okay, how about, I'll do the E first. So S gets replaced with 0, 1, x. X itself gets replaced with 0x. So that gives me 0, 1, 0, x. And finally, x gets replaced with 1. And then this one is just kind of more tedious. S gets replaced with 0, 1, x. Here I once again replace x with 0x, but now I replace that x with 0x again. So 0, 1, 0, that x becomes 0x, and then again. And I get 0, 1, 0, 0, 0x, and finally, maybe I'll just squeeze it in here, I get 0, 1, 0, 0, 0, 1. And there it is. Cha. Okay, good. So yeah, 1, 2, 3, 4, 5, 6 steps, 5 derivations. Okay, that's one number down. More to go. Good. Woo. 6, I found really hard. I spent a lot of energy trying to figure out what this grammar does, and I just got really confused and made a bookmark to, revisit this once I learned some more theory. So what was this problem? This problem number 6. It said, okay, sigma is A, B, C. The set of non-terminals, okay, you don't really need to tell me that, but it's S, W, X, Y. And now here are the rules. There's like a lot of them. So S goes to B, W, or CX, or AY. And okay, now since the alphabet doesn't include zeros and ones, this one is not confusing me, so I am back to the OR notation. W goes to B, W, or AY. X goes to AX or B, and Y goes to AX or CY or C. That's pretty hard. And I went to go try, I guess I should just be honest and do this. I went to go try to understand this, and I said, okay, oh my gosh, what are we going to do? I have an S over here, and then so many different things can happen. It can go to a BW, or it can go to a CX, or it can go to an AY. And now I started to produce the BW. One second. When I went to go produce the BW, I saw something very sad, which is that BW goes to either BW, so I end up with a BBW, or that W gets replaced with AY. But now, well, at least one of these branches I'm comfortable with, because the W can once again be, can get replaced with BW, but then I still have this kind of B, and then that W is getting replaced with AY. And so, yeah. And so, here maybe I put like a kind of a green around this Y for a minute. I think I understand to an extent the W symbol, which is that one option is that it just keeps outputting B's. But how does it ever stop is a good question. And then there's also this sort of branching that happens, which is that I begin following the Y variable. So I better understand what that Y non-terminal does before I continue on in this branch of the tree at all. Ugh, this is terrible. Okay, well then let's look at maybe CX next, because X has the nice attribute that it does have a rule which leads to a, it does have a rule whose right hand side has no non-terminals, which is to say it has only terminal symbols, so it terminates. Okay, so X is one of the ways to like end. So maybe that's a good place to start. Okay, so I make this tree and I get, well, what can X do? It can just stop with a B. Okay, so I finally got a string now, CB. But what's another option for CX? Well, I get C, the other option for X is that it goes AX. Okay, well now I'm feeling like, even though this is infinite, I feel like I get it, because, well, once again, what can I do with this X? It can be either AX or B. So I get CAB, and I get AX. And so, and this process continues, right? CAA can end in a B, or it can continue. So it seems that this path in the tree, at least, is going to produce strings with C, some number of A's, followed by a B. Okay, but there my piece kind of ends. Piece as in understanding, because now I don't know what to do, right? Now I get sort of A, what can Y do? Well, Y can go to C, Y can go to CY, so that's kind of depressing. or it can go to just C, or it can go to CY. Oh no, sorry, I did that one. Or AX rather. So AX, and it's at this point that I just kind of gave up on this method. And to the extent that this is a method at all, it is a kind of a method. It's served me pretty well in the past, at least as long as the grammars were pretty simple, which is to make a decision tree. But you know, these decision trees have this feature in which they sort of loop and they kind of explode in size. And I have lost, maybe I'm just dumb, but I have lost the ability to understand what's going on using this approach. And so I pause and I ruminate that, man, I really wish there was some sort of algorithm for converting a regular grammar into some object with some finite representation, and there is one, and it's the subject of next week. But if you had asked me to describe all the strings that this grammar generates, I would have a hard time doing that, at least following this method. And so I abandon this attempt, and I just go back to remembering, hey, what is this problem actually asking me again? Oh yeah, this problem is asking me not to solve all of the world's problems, but merely to investigate whether three particular strings can or cannot be made by this grammar. And C, part C, 6C, gave you the string BB, ACAB. D gave you the string BB, AACB, and E gave you the string CAABB. Okay, so instead of doing this problem in general, maybe I'll just solve the problem I'm being tasked to solve, and maybe it will be possible. And it just turns out to be possible. So let's go. Let's attempt to produce a derivation of these. Okay, so I start with my start symbol, and well, to make this, this is 6C, 6D, and 6E here that I am. This is just what's in the book. These are the strings I'm investigating. So okay, in part 6C, I need my first character to be a B, which means I just have to follow the BW rule. And okay, now the next character also needs to be a B. So I'm on W now. Well, I just have to do a B again. Or I have to follow rule BW. So I replace W with BW. Okay, and now the next character just needs to be an A. I gotta write smaller. The next character just needs to be an A, and there's only one rule to write A from non-terminal W. It's AY. So I now perform the BBAY. I substitute for W, AY. Okay, now I'm here in Y. Well, the next character has to be a C. So I have two choices. Well, end the string, that doesn't work. So I need to do C. I need to follow this one, CY. So I replace BBA. I replace Y with CY. Now, and now I have to get, if possible, an A out of this. And there is a way to do that from Y. It's to follow the AX rule. So I get BBAC. In place of Y, I write AX. And BBAC. And then the final thing to do is to just use the X goes to B rule. And so, okay, just by tracing through this, I have achieved success. And so the answer is, yeah, you can do this one. Good. What about D? Okay. Well, it seems like it would be harder in general to prove that you can't produce a particular string with a particular grammar, and that probably is true in general. But here, we begin. So once again, I need to start with BBA. So actually, almost all of this is the same, because my choices were completely determined by those first three characters. So B, B, W, B, B, A, Y. But now, when I go to do my Y, my next character has to be an A, because I'm trying to make BBAA now. So I have to use the AX rule, and so this becomes BBA. In place of Y, I write AX. But now I need a C, and it is now when I just stop and I'm sad, because let's trying to draw. I don't know how to draw crying. That just looks like a nose. Anyway, I'm sad because I cannot use non-terminal X to make my next character be a C, and so there's just no way to produce this string, because there's only sort of one path through this grammar, which starts with BBAA, is essentially what it boils down to. And okay, something similar happens in part E. If I tried to make the string CAABB, it's fairly deterministic, which is to say that I have to start out of the gate with, I have to replace S with CX, and then if I need the next character to be an A, I have to replace X with AX, so I get C goes to AX, and then I get CA. Well, I need the next character to be an A again, so I once again need to replace A with AX. Now, I need the next character to be a B, but there's only one way to get a B out of non-terminal X, which is to just end it. So I can make CAAB, but I can't make CAABB. And so the answer is, no, you can't do this. Okay, good. That I thought was actually the hardest part of the homework, was kind of tracing through someone else's grammar. The more, what you would think of as being more difficult part of the homework was to write well, let me not get ahead of myself. Possibly there are more grammars to go. 7A says, I'm just going to keep using purple now. 7A was, yeah, it is another grammar, but now we are being given the hard task, which is the task of describing the grammar, but I guess it's just not hard somehow, so it's not hard. Okay, so sigma is ABC, that's good to know, and here it is. S goes to AX or BY, and Y goes to BY or B, and X goes to AX or C. Okay, and here I'm just going to make the tree, and okay, I just do it. Here's S. What does it do? It goes to AX or BY. And there's just not as much looping going on here, so this is just baby stuff now, right? What does Y do? It goes BY or B, so this is just going to either end BB or it's going to go BBY. And what does BBY do? It goes BBB or it goes BBBY. And AX is only slightly more complicated because what's that going to do? It's either going to go, X is going to go to C, so I just get AC, or it's going to go, X gets replaced with AX, so it's going to go AAX, and then we're going to get either an AAC out of this, or an AAAX, and so there it is. Woo! I am now prepared to give my answer to this problem, and here it is. Here's my answer. Just more clarity here. And now I'll use the full-on regular expression notation, which you're going to learn later in the week. I guess I will. It's going to be, well, I have to have an A, at least one, and I have to end in a C, this is one option, with some indeterminate number of a's in the middle. So you can say this is going to be of the form a star. Actually, I guess I'll just keep using ors. So it'll be a star, followed by a c, or okay. Yeah. It's this vertical line is sort of said or. So this is okay. So it's going to either be of the form a star c, or it's going to be a bunch of b's. But how many? At least 2. So this can be written as b star. And I think that's just right. The alternative way of answering this problem is to use the plus notation. So then that's a plus c, or b plus. But I don't know, the plus notation, I guess it's cool, but it's not going to change my life or anything for the better, so, you know. Whatever, I don't really need it. Okay, 7b says s goes to ax or by, y goes to by or c, and x goes to ay or a. Okay, let's similarly make a picture for this one. Well, here is my start symbol, making this decision tree. Yeah, and we go either ax or by. What does by do? Well, it's not too complicated. It's going to just keep making b's or end in a c. So we have the keep making b's option. So y gets replaced with by, or we just end it with a c. And then here, again, we get BBC or BBBY. But what about X? X really doesn't do much. No, okay. By that I mean, yeah, I only get to use that non-terminal like once, essentially. And it becomes either an A, so I get A, or it becomes AY, X becomes AY, so you get AAY. And now we just kind of follow the Y loop or something. And what does Y do? Y, if you ignore these B's, Y is just going to do that. So, what is this language doing? Well, one option is it could just give you 2 A's. Another option is it could give you 2 A's followed by whatever Y does. And the other option is it could give you a B before whatever Y does. And what does Y do? Y, this is a little misleading, Y produces a C with some number of B's in front of it. Okay, so to try to explain that all again, either we have AA, I think this is the best way to do this, or we have AA followed by Y, and what does Y do? As we just said, Y is some number of B's, 0 or more, followed by a C. Or we just go directly to the right branch, which is to say we begin with a Y, and then we do whatever Y does, and what does Y do? It produces some number of B's followed by a C. So this is the one option using regular expressions. If you want to use pluses, because that just makes you happy, then it makes me sad, but there it is. You would just write B plus here. C. Okay, that's it for 7b, and then it's not till the sort of very end of this homework that I am given the task of writing a regular grammar. That's what 9a and 9c are, and okay, they're just both not that hard, so we're almost done, actually. Okay, 9a says, how long is the video? Alright, 9a says, let's consider the following language where Okay, first, so let's see. Sigma is composed of A's and B's, or the alphabet is A, B, and let the language be all the strings from, over that alphabet, as people say, where W does not contain the BB substring. Okay, so we can't let our grammar produce a string with two B's in a row. Alright, I think there's a lot of different ways to do this, but I hope my way is right because it's very short. And that is to say, I shall do the following. I shall say, okay, look, I can either start the string with an A or a B. So, what if I started with an A? Well, if I started with an A, I'm sort of free to do whatever I want next. So let me sort of think of this as being let me create a new non-terminal in my mind, big A, which to me captures semantically the idea that I just did an A. Okay? And the other option is that I come right out of the gate with a B, and then I go I create a new non-terminal, big B, which I intend to capture the idea that I just made a B. Okay, then I don't want to forget, I almost did forget, but let's not forget that it's also possible to just it should be possible to make the empty string. And here we get into a kind of weird meta philosophical problem, which I am, being a mediocre philosopher, I was able to work my way out of, and I think gossip just is bad sometimes. Love you, gossip, but sometimes you are bad. And one of the bad things he did, which I rambled about a lot in my video lesson on grammars, is that he continues to refer to this sigma as the set of terminal symbols. And that is, I think, misleading, because if you are going to introduce your grammar by just saying, hey, here are the terminal symbols, here are the non-terminal symbols, then you're sort of using as your fundamental objects kind of like the symbols of your grammar. But hey man, shouldn't we talk about, like, the letters of the alphabet? And so I went out of my way, possibly overboard, to call this sigma the alphabet, and I really want to think of this as the set of characters which are going to appear in the final strings. I mention this now because Gossett wants to use lambda as a terminal symbol, as well he should. It is a terminal symbol in a kind of a way, in that it terminates the string, and so I agree with him that we should consider it a terminal symbol. But I disagree with Gossett that we should ever explicitly include it as one of the elements of sigma, because it's just not a character of the alphabet of strings which we are creating. It's merely a symbol which we use to write our grammar. And so, previous years have erupted